All right, welcome, ladies and gentlemen. So today we are talking about composition of functions, and the way I imagine functions are as machines. So here I've got four separate machines: f of x, g of x, h of x, and j of x. So this, you could also call this the +3 machine, right, or the ×4 machine. So anything that goes into these machines, out pops whatever it was plus 3. All right. So that's kind of the idea of what we got. So let's see. Let me grab a snapshot of this one. So suppose, I don't know, maybe we work at like some factory or something with all these machines, and we're just like hanging out, and we're interested, what sort of things can I put into these machines, and what sort of things what sort of things come out of these machines. So let's just do some practice with this +3 machine, f of x. So if I plug in 3, what do I get? 3 goes into the machine. What pops out of the machine? 6, right? It just added 3 to it, right? So that would mean that f of 3, right, is equal to 3 plus 3, or 6, right? So let's try, what if I plug in 0 into this machine? What would pop out? Yeah, just regular old 3. So if I plug in 0, I get 3, so that's cool. What happens, and then sometimes it's interesting to toy around with machines, try to figure out what could break the machine, different things like that. What if I plug in like -7? Right? As long as we're hanging out at the factory on our lunch break, we just start like throwing like sandwiches into the machine and like all sorts of stuff. Just tinkering around, right? Yeah, let's see if we can break this machine. Does this machine just accept any input, right? What happens if I plug -7 into the machine? Let's see, -7 plus 3 is -4, right? So, all right, I guess as long as we're okay with negative numbers, right, that seems to exist. So f of -7 is equal to -7 plus 3, which is -4. What if I wanted to find out what would I have to plug into this machine in order to get 0 back? Like -3. Right? Yeah, -3. Right? So, I mean, I can even kind of have a little bit of forethought here and work like that. So let's see. So f of -3 happens to be -3 plus 3, and that's a 0 of this function, right? So now, what if I want? Could you describe what kinds of numbers I could plug into this machine? What are the possible numbers? Are there any limitations on what I could plug in? I mean, we tried positives, we tried negatives. I mean, I could even plug in like the square root of 2. I would just get the square root of 2 plus 3, which that number exists, so that's fine. I could plug in fractions, right? If I plug in a half, I'd get 3.5, right? Or 7. Well, I guess if I believe in imaginary numbers, I would get 3 plus I back. Yeah, so I mean, it would just give me an imaginary number back. But as far as plugging in like real numbers, I seem to get real numbers back. Do you guys know what the word domain means? Domain of a function? Maybe I should define that first. I think I shall. Let's see. So domain, it is the list, or the set sounds fancier, of all possible inputs into a function. And domain actually has, like, unfortunately, I think there's 3 ways that you can represent domain. It's usually represented by a D, like a colon, something like that. And there's a bunch of different ways you can represent it. So if I said the domain was from 3 to 8, like this, and one had a square bracket and one had a closed parenthesis in that case. A square bracket indicates that it includes the 3, all right? So it's 3 all the way up to 8, and the open parenthesis, or closed parenthesis in this case rather, means it includes everything up to 8, but not 8 itself. So that's one way you could represent domain. Another way I could represent the same thing, I could say 3 is less than x is less than 8. All right, so that's a third way, or second way. I guess I have to count here, right? Second way you can represent domain. And then a third way, so it's just a matter of notation, 3 different ways of writing it. They all represent the same thing. You can say that the domain is the set of all x such that 3 is less than or equal to x is less than 8. So this is set notation. So this is read as the set of all x such that ... Okay, and that's what just kind of like this part here would be interpreted as. So like this little like weird absolute value bar thing just means such that. And then I've got some sort of restrictions on that. Okay? So the domain in this situation, maybe I can fit it over here. That makes sense. Are there any limitations on what I could plug in, right? It seemed like we could plug in everything. So I could say that it is basically the set of all x such that x is anything, right? There's no restrictions. I mean, I can plug in whatever your heart desires, right? And then there's the concept of range. All right. Oh, actually, before I go on, I just realized another way I could think about inputs is x values. All right, the possible x values of the function. And then range is very similar to domain. I guess I'll go with green again. Range is, I don't know if you guys could guess what range would be. It's somewhat complementary to it. Any guesses? It's the set of all possible... No guesses? Outputs. Yeah, that makes sense. Of a function. Right, and those outputs could also be considered y values. Right? And mathematically, the word range does have 2 definitions. In the realm of statistics, if I have a list of numbers, the range is the highest number minus the lowest number, right? You might remember that. In the world of functions or graphs, it's talking about the possible outputs or y values. Okay, so just be aware. Sometimes mathematicians use different stuff. So if I have, how about this for a range? What if I go from 0 inclusive all the way to infinity? Here's one way I could represent range. I could represent that same range as being, how would you describe that as an inequality? From 0 to infinity. Well, actually, we wouldn't have to include a less than infinity thing. And actually, I just realized I had already written an x there. But since we're talking about y values, I guess I technically should refer to y here. Yeah, just y is greater than or equal to 0 would include all the way up to infinity. So yeah, I wouldn't need to put less than infinity there. And then to represent that in set notation, I would say this it's the set. Let's see, I'm usually pretty good with curly brackets there. The set of all y such that y is greater than or equal to 0. Let's see, yeah, I'm not a fan. There's an alright one. I gotta get into the swing of things on my curly brackets. Takes a little practice. So, regarding our +3 machine, what kind of range do you think this has? I mean, we asked the question earlier, what would I plug in to get 0? I don't know, what would I plug in to get 10? 7? What would I plug in to get -21? -24. I don't know, it seems like I could get anything, right? So yeah, it turns out the range in this case is everything. So it's the set of all y such that y. Alright, basically anything. If I wanted to represent that with a parenthesis notation, I would say from -infinity to +infinity. And you always use open parentheses on infinity because it can't equal infinity. So we use like up to infinity. But that kind of, I guess. Right, yeah. Well, just keep going. Yeah, it's kind of like giving. Yeah. You'll just take a turn, left-hand turn, quarter mile. Keep going, you'll find it. You'll get there. You'll spot it. You'll know when you've gone too far. Or maybe you won't. I don't know. That'd be crazy. So there's kind of just some inputs and outputs. We've also represented inputs and outputs a couple different ways, right? 3, 6, I also could represent as 3, 6. I also have represented function inputs with a little table, little input-output or XY table, right? And you could have input of 3 gave us 6 as an output. And then there's even like this other weird, I'm not a fan of this as much, but this weird like oval thing that people do where they'll have like an oval here and an oval there. And then like they'll have some of the inputs of like, what did we plug in? I'm just going to do 3, -7, and 0. And then like, so here's the inputs over here. Inputs. Outputs. And then the outputs would be like, I don't know, 6, and then let's say I had the -4 here and the 3 here. Someone's excited. So let's see, and then like they have like these weird little arrows. So like 3 gave me 6, and -7 gave me -4, and 0 gave me +3. Have you guys ever seen those charts ever before? Well, actually, maybe I've gone too far ahead of myself. I believe this is, you might have seen this elsewhere, but the definition of a function, maybe we haven't defined it yet, or you and I haven't. The definition of a function basically is relation, or kind of like relationship. A relation is just, any sort of connection between inputs and outputs. So a relation in which each input has exactly one output. So I guess I might as well define that. So things that, I'll draw my little oval thing again. So what if I've got 2, 1, 3, and 0, 4? And actually I'm going to grab a snapshot of this. I'll show an example and a non-function example. Man, I like how I can just duplicate stuff so quick. So let's see. So would this be a function, do you think? So these were my inputs, and here are my outputs. So does each input have only one output? Right? Like if I said, all right, with this function in mind, I give you 2, what do you give me back? 0. I give you 3, what do you give me back? 4. If I give you 1, what do you give me back? Right? So even though 1 and 3 both happen to give 4, that's okay. It's still a function. I mean, even in terms of parabolas, we've seen the same y value show up twice on a parabola, and that's okay. It can have the same output, right, multiple times. Whereas this would be an issue, because now if I say, I give you 1, what do you give me back? Right? Some people would be like 0. Others would be like 4. Some people would be like 0 or 4. Some people would be like 0 and 4. There'd be some confusion. So this is not a function. Okay? So because there was 2 outputs for a single input. All right, graphically speaking, there's this thing called the vertical line test. I'll show you a function and a non-function here. So check this out. Here's this crazy whoop, swoop, swoop-dee. And this is a function because of what's called the vertical line test. Any line I draw will hit only at most a single point. 1, 1, 1, 1, 1. There's no vertical line I could draw that's going to hit more than 1 point. Whereas if I draw something like this, maybe like a sideways parabola, which we'll talk about in Math 4, those do exist, they're just not functions. All right? Now this is okay. That vertical line hit no points. That's fine. That's not why it fails the function test. Now this is okay. That vertical line hit 1 point, so there's no problem there. But then, this is where we messed up, right? Because what if graphically this was like at -1, this was say +5, this was -3 or something. If I said I give you -1, what do you give me? Your outputs are 5 or -3. It's not a function. All right, so it's kind of how we classify functions. Not too big of a deal, but I guess I might as well, give you that little background check there. So let's grab a snapshot of some of these other machines. I might just skip right to this one here, the old h of x machine. Oh, I guess I don't have to do that. So let's see, paste, yeah. And here's old h of x. So let's do another example. So let's plug in some values here. So I plug in 2. What do I get? 4, right? 2 squared is 4. Makes sense. I plug in a 0. What do I get? 0. Okay. I guess we can write some of this down. So h of 2 was 4. H of 0, I guess I could write that out, is 0 squared, which is 0. I plug in -1. Right? Because -1 all squared is +1, so h of -1 is -1 squared, +1, right? Not that bad. And then what if I want to figure out what is, how about h of like, I don't know, -5 or something? -5 squared. What's that going to give us? 25? Yeah. Right, negative 5 goes in, 25 pops out. Great. So looking at this function, what do you think the domain is? Is there anything I can't plug into this machine? Wow, it seems to accepts everybody, right? So the set of all x such that x is anything. How about the range?
No, it can't be negative.
Yeah, this machine will never give us a negative number. Yeah, so how would I describe that? What's the restriction you'd say? Perfect. All right, so that would be my range. Man, I'm getting better at my little curly brackets. I also rolled my R quite nice there. Range. Although you wouldn't have to roll your R when saying the word range. But I just did. Somehow I feel like the curly bracket is the graphical equivalent of rolling your R. I don't know. It's fancy. So let's say, so one night you're working late at the factory. And you and your buddy, right? The bosses went home already. You guys are like kind of perturbed that they made you work late, and you're just hanging out. You know, maybe you finish the job that you were supposed to do, and then you guys start deciding, hey, let's have some fun. What if we set up these machines so that what goes into one machine and out of the other will immediately fall into a second machine, right? So you guys are just like messing around with the factory equipment, and so like I don't know, you build like a little platform here, I guess. So this could happen. So here's a little platform, and so yeah, so you guys are like, man, this is going to be awesome. So we've got what is this? This is g of x, and this is what was that? H of x. What one's the squared one? H of x? Okay. So watch this. Here we go. Now we're going to have some fun. Bosses are gone. We're just like fooling around in the machines. We're going to throw stuff into the machine, see if anything breaks them, right? So let's plug in 2 here. 2 falls into the +3 machine. What pops out of the +3 machine? Like that moment before it falls into the squared machine? All right, 2 + 3 is 5, right? So 5, so you see it, and then it falls right into the x squared machine. I mean, you can just say, oh, boss, it happened. I don't know, like it fell out of one and into the other. Right? So what happens here when 5 falls into the squared machine? Right? Perfect. So to describe this situation, it looks like I could scroll over a little bit there. Nope. Oh, no, my page is all messed up. Oh, well, watch this. I'll just fix it like this. Example, bam, now no one ever knows I did it wrong. So let's see. So the way I would write this, actually I gotta, never mind, I gotta undo those, blah, 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 blah. So let's see, so we're plugging in 2, up too far. So we figured out that g of 2, was 2 + 3 or 5, right? That's what g of 2 was. And then we figured out that h of what? H of 5 was 5 squared or 25. So now the mathematical way of writing this, when I'm using multiple machines here, I would say, this is the way you could write it. H of g of x. Well, I guess technically h of g of 2, if we wanted to be specific. And what this means is when you're doing function composition, that's what this is referred to as. When we're combining functions, we're composing new functions out of previously known ones. You start at the innermost component. So you take the 2, plug it into function g. And then whatever you get from that, in this case 5, you take that and plug it into function h. Okay? So h of g of 2 means you take 2, plug it into g, we got 5. And then take 5, plug it into h, we got 25. So h of g of 2 was the 25 we were referring to, right? So yeah, let's try plugging in something else. What if I plug in, I don't know, -7? What pops out of the +3 machine?
16. Oh, whoops, I did the bottom.
Yeah. So -4. And then -4 squared is 16, right? So to phrase that question, I'm asking, what is h of g of what was it? 7. I already forgot. And the way you could calculate that is in 2 steps. That means take -7, plug it into g. So g of -7 is -7 plus 3. And that's -4, right? And then take that -4, right? The moment it fell out of that machine, it's going right back into h of x. So h of -4, sorry, is -4 squared. Hello.
Hi, could I see you for just 1 minute?
Certainly.
Because I'm trying to schedule stuff.
How can I help?
Next Tuesday.
Well, I don't care to have that, but I might have them do this project on Saturday when you go to
Was I driving?
That's what you were like, oh, what's that? You're tire when you get to the car.
Oh my god, that's so
Yeah,
okay, first of all, your horn sounds
Your
weird.
horn
I
sounds
know, it's
weird.
not stupid.
Okay, because we thought that was like the car.
I was like,
made
is my
some weird
tire like rubbing on my
thing? Because that's what it sounded like. It was the most
And
weird
I
thing
literally like
ever.
freaked out.
Yeah, she freaked out, and then you were like, it's probably like something that we in the car when she makes a turn. Ew, your horn sounds so dumb.
What happened to his horn?
No, it's like me and I thought it was my tire.
Yeah, it's disgusting.
This is like,
Wow.
wow.
That's alright, it's just
Okay, let's see. So that occurred at around 28 minutes. So I'll have to edit that out of the video.
Yeah.
All right, and we're back. So ladies and gentlemen, so we just figured out that h of g of -7 was 16. All right, so that's what we just did. Now, now after tinkering around for a while, like I don't know, have you guys ever seen like a TV that also had like a VCR and a DVD player all built into it?
yeah. My dad is.
What if we just like all right, get like a bunch of us, and we just like put this machine like on top and just start like stomping the x plus 3 machine into the x squared machine. We just like combine them, right? We're like, forget this. Like, it was difficult building this shelf. Let's just like stomp one into the other. All right? So that's what I'm thinking. So what we would have, I guess I can erase my little circle there. So h of g of x, I'm literally putting the g of x machine into function h. Okay? So what is h of x normally? It's the x squared function, right? So x squared, and whatever is inputted, we square it. And this time, what are we plugging in? We're plugging in the x plus 3 machine. So the entire thing going into this is x plus 3. All right, so I literally fit an entire machine inside of the other one. Craziness, I know. So let's simplify this. X plus 3 all squared, does anyone know what that becomes? There's a 90% chance that whatever you say will be wrong if you don't remember something.
You can't distribute it over a plus.
Right, okay, whew, all right. We can't distribute an exponent over a plus sign. So I could either do x plus 3 times x plus 3, or if I square it using a pattern, I'll end up with x squared plus 6x plus 9. All right, so I end up with an entirely new machine. It's like a TV, VCR, DVD player, right? It's one of those things. So great news. We just made a new machine, right? The bosses are hopefully going to be thrilled about this in the morning. Who knows? But now we have this thought. It turns out that in case one of these machines broke, the bosses had like some extra ones in the warehouse, so that way our productivity wouldn't fail. And we just suddenly asked the question, what about g of h of x? Is that going to give us the same thing as the h of g of x machine? What do you guys think? So what is the g of x machine? X plus 3. So you take its input and you plus 3 it, right? And what are we inputting into g of x? Yeah, we're plugging in this entire h of x thing, right? We're plugging in x squared into g of x. So this is x squared and then plus 3. So what does this become? There's not much simplifying that takes place. Yeah, just x squared plus 3. And so now we suddenly realize, wow, those are two different machines. Well, hopefully not. We'll see what happens. But, wow. We're figuring something out, though, on the company's dollar. So, yeah, h of g of x is not necessarily equal to g of h of x. Interesting. And actually, the domains of these two functions happen to be all real numbers, but the ranges of them are interesting. Both of these happen to, graphically, we would recognize these as parabolas. This one, y, could not be anything less than, oh, wait a minute. Oh, wait, what's y going to be? Yeah, y wouldn't be anything less than 3, right? So y is greater than or equal to 3. This one, we'd have to find the y-coordinate of the vertex. It'd be a little bit trickier, I think. Let's see, -3. No, this one actually could be as low as, no, it might even be able to be lower than that. I'd have to think. This one might be able to go as low as -3, but I'm not certain. But anyways, but yeah, so we'd be able to do all sorts of crazy work with these. Now, it turns out there's also this concept of inverse functions. And those are functions that undo one another. All right, so we have our plus 3 machine, so the inverse of the plus 3 machine, like say we put something through it and we're like, oh no, I didn't want to do the plus 3 machine. Like, what could I take that thing and put it into that would undo what I did, if that makes sense. Right? I'd need like a -3 machine, essentially. Right? Right? Makes sense. Or if I have like a multiply by 4 machine, what's the inverse of the multiply by 4 machine? Divide by 4 machine. Perfect. And I think we might have some functions that are inverse functions here. Which of these functions listed are inverses of one another? Yeah, these two guys, right? Those might be inverses of one another. And I want to show you something interesting regarding, well, I don't know how interesting, but it's something. Let's see. Regarding function composition with machines that are inverses of one another. Let's see. So let me write the old example up here. EX in a box. Damn. So let's see. Let's figure out, if you guys could, tell me what h of j of x is, and tell me what j of h of x is. All right, because previously we found out that those are not necessarily the same thing. But in some occasions they might be. Actually, now we theorize that these two are inverses of one another. What do you think these might equal? Anyone have any thoughts? Let's figure this out. So h of x is the squared machine. So whatever I plug into it gets squared. What am I plugging into it? The square root of x. Yeah. Actually, oh wow, I just thought of something. This might technically be the absolute value of x. So these might not be the best examples of inverses, right? Do you guys remember that back in the day when we were like simplifying radicals and exponents, and we found out like even ones had absolute values, right? Because squaring it and square rooting it, ooh, man, oh, this one's real ugly. Whew. Yeah, because actually this one doesn't even allow negative numbers to be inputted into it. Because if you plug a negative number into the square root machine, it gives you an imaginary number. And your boss would be real unhappy, like, I just dumped like a whole bunch of stuff into the square root machine and then nothing came out. It's imaginary, I'm sorry. Like, he wouldn't be happy about that. Like, you just turned a bunch of his product into like imaginary product. Like, that wouldn't be good. No. So this one's a little bit weird. Well, yeah, I suppose, but it's too late. We'll just roll with it. We'll just pretend it's x. We'll just put x in quotes. We'll pretend, for sake of example. Classic Mr. Y. So anyways, and the j of x machine is the square root machine. And what am I plugging into the square root machine? X squared. And the square root of x squared is, yeah, we'll call that x. Technically, that's also like absolute value of x. This one actually would be absolute value of x. This one would would be absolute value of x with then some restrictions because some of it would be imaginary. It'd be weird. But, yeah, I'll just call it whatever. That's fine. But yes, poor example, my bad. But nonetheless, inverses, if you have function composition between inverses, right, +3 machine, -3 machine, if I +3 and then -3, it's giving me back x. It's giving me back the thing I started with. It was the goal of this. And then it didn't work out. So, my bad. But what I would like to point out is there's one more type of notation regarding function composition. Let me pick a nice color here. So h of g of x, the other way that you might see it written is h little circle g of x. And it means exactly the same thing, It doesn't say hog, and that's not a letter O. That's like, it's like at the level of a little multiplication dot, except instead of a dot, it's like a tiny circle.
So like degree sign, a little lower.
Yeah, like the degree sign hanging out in the middle height right there. Perfect. I love it. Man, these are the best descriptions ever. I love it.
Degree sign that's not all the way across.
Yeah. It's a short degree symbol. What was that?
What does this represent?
It means composition, right? So this is identical to this. It's just another way of writing it. It just means h of g of x. Actually, you could almost think about it as like a little O in the word of, if the word of was tiny and tall, and the F wasn't written. H of g of x, yeah, it works. But yeah, it just represents composition. So there you go. So that kind of covers all of our stuff about composition, domain and range, etc., etc. So I think we'll have an opportunity for some partner work. I'm going to have to go back and make sure that that conversation was not recorded.
Totally feel it.
It'd be good. Oh, that sounds great, buddy. And then we'll come back.